Hey all, good evening. I hope I'm audible. Can you hear me? Great. So, how's the camp going? Coming towards an end. I hope you've learned quite a bit till now. So let's just wait for a minute or two for some other people to join, and then we'll get started with DP. Good evening. Good evening. That's very good to hear, Dipanshu. Great, great. Hey, Sachin. Shubham, I think most people are able to hear me. You might want to refresh your tab, or maybe just try increasing your volume. Great. Okay. So let's. I hope people on YouTube are also able to hear me, even though I can't actually see it. Cool. So let's get started. So dynamic programming, right? So this tends to be a topic which a lot of people are kind of afraid of at the beginning, but I actually don't think it's that intimidating a topic. There's not a lot of theory behind DP which you need to learn. So many topics in computation in computer programming, there's some bit of theory that you need to learn, and then you start solving problems. So something like graphs, or even sorting for that matter. You learn some theory, and then you get to solving problems using the knowledge you have. But DP, on the other hand, there is theory. There is actually some deep theory, but almost no one in computer programming actually uses that theory per se. It's more of just a technique to solve problems. So what we'll do, we'll not go into the theory per se. So if you're actually interested in the theory, you can look it up. The things called optimal substructure and overlapping subproblems and things like that. It's simple enough. There's actual deep theory behind that as well. But I personally don't think that helps very much in computer programming. So what the agenda for today will be, we'll be looking at a bunch of problems, very classical problems, and we'll see how to solve them. And the hope is, towards the end, you get a feel for, so all of them have kind of like a similar flavor or a similar process to solving the problem. And the aim is to kind of focus on that, and hope you take away the concept of DP from that, right? So that will be, so it'll be very heavily problem solving based. And so let's get started. So first, let's start out with a very toy problem. Okay. So you're given n integers, a1, a2 to an. So this is a sequence, right? And the question is, find a subset of these elements which has the maximum sum. Okay. So what would you do for this? Let's say the numbers are let's say the numbers are 5, minus 3, 4, and 9. What is the answer for this question? Correct. Exactly. Yeah. So all of you get it perfectly correct. It's not just 5 and 9, right? You can also take 4. Just take all the positive numbers, right? It's just 5 plus 4 plus 9 is 18, right? That's it. There's no twist or turn to this problem. It's as simple as, given n integers, find the maximum subset. So I'm just going to take all the positive integers in it. I don't want the negative numbers because that reduces my sum. I just take all the positive numbers and find their sum, right? And that's going to give my answer. Very trivial. There's just almost nothing to this problem, right? So now let's go to the actual problem, which has a slight twist. So now I can't pick any subset. Instead, there's a concept of validity. What does it mean? a subset is valid only if I don't pick two consecutive elements from the same, from that set, right? So now I want a subset. Again, I want to maximize my sum, but then I have this extra constraint that no two consecutive elements can be chosen. Okay. So in particular, if I have some 10 numbers, the subset A1, A3, A5 is a valid subset, whereas a subset A1, A3, A4 is not valid because A3 and A4 are consecutive, are next to each other, right? What is A? But A is, there is no A. A is like, think of A as an array. You must have seen arrays by now, right? So think of an array of size n, one indexed. So I have A1, A2 up till AN. So I want to find a subset of that array, right? Or you can think of it as a sequence or an array. Yeah. So there is a concept of order to this. Okay, Himanshu, that's an interesting approach. We will come to that. Yeah. So right now, is the problem clear? So for example, let's take the sequence or array 2, 4, 5, 1, right? If this was the input for the previous problem, what would have been the answer? I would have just taken all the numbers, right? Because all the numbers are positive, and if we didn't have the constraint, I'm just going to say the answer is 2 plus 4 plus 5 plus 1, which is 12, right? But now I can't take all the 4 elements. I can take at most 2 elements actually, right? So yes, just see the example I'm giving. So if the array is 2, 4, 5, 1, the question now is to find a subset of these 4 elements which maximize the sum, and no two consecutive elements can be chosen. So 2 and 4 I can't choose. I can't choose both 2 and 4. I can pick at most one of 2 and 4. Similarly, with between 4 and 5, I can pick at most one. I can't pick both 4 and 5 in my subset. Similarly, I can't pick both 5 and 1. I can pick at most one of them, right? So yeah, so that's the question. And here now the answer should be clear, right? I mean, I'll choose 2 and 5, and I get 7, right? And this is a valid subset because 2 and 5 are not adjacent. Whereas I could have said, why not pick 4 and 5? I'm not picking them because they are consecutive, so I can't pick them. So 4 and 5 will be an invalid subset in this array, whereas 2 and 5 form a valid subset. And you can see that amongst all the valid subsets, 2 plus 5 will be the maximum. What are other valid subsets? 4 plus 1 is another valid subset. 2 plus 1 is another valid subset. Just 2 is another valid set. Just 5 is another valid subset, right? But you see that there is no valid subset with 3 elements. You can't have a valid subset with 3 elements in this given array, right? Because amongst 4, if you pick 3, there will be at least one adjacent pair. You can figure that out, right? So in this case, the answer, it turns out, is just the first and the third element that gives us 7. So now the question is general. So given any general array, find the maximum sum possible. So any ideas? How do you go about doing this? So okay. Abhinav, no, there is no constraint that you can choose only 2. You can choose as many elements as you want. The only constraint is that you can't choose 2 consecutive elements. If you're able to choose 3 elements such that no 2 of them are consecutive, you're totally fine with choosing more than 2. Yeah. Okay. Anant has an interesting suggestion. We'll get to that. Yeah. Okay. Suvid also has an interesting solution. Okay. Cool. So a lot of people are saying brute force. Okay, so Rajeshri, you're saying you'll sort the array and then find the alternate elements, but that doesn't work, right? Because once I sort, I kind of lose the adjacency, right? I mean, the adjacency, when I talk about consecutive elements, I talk about consecutive elements in the original array. After I sort, I if I don't keep track of which were consecutive earlier, I can't use it later. Right? So that's one major issue. Okay, so Kanak is saying something interesting. So he's kind of trying to figure out what is the maximum number of elements you can choose. That is a interesting question to think about. So let's answer that first. Given 4 elements, do you all agree that the maximum number of elements I can pick in a valid subset is 2? I hope everyone agrees with that. Yeah. Oof, there are a lot of, yeah, okay. So in general, suppose I have an array with n elements, what is the maximum number of elements I can choose in a valid subset? Not exactly n by 2. There's a bit of a twist to this. It's not even n by 2 plus 1. Okay, yeah. So Dark Knight has gotten it perfectly right. Okay, all of you are very near the answer, but it's not exactly right. Okay, Sai also has an interesting thing, but it's slightly wrong. Just think about it a bit more. Yes, Himanshu has gotten it correct. Sidra. Yeah, it's n by 2 plus or minus 1 or n by 2. It's something along those range, right? But what exactly is it? Okay, Surabhi has also gotten it correct. Okay, so let's just take an example. Suppose there are 5 elements, right? A1, A2, A3, A4, and A5. What is the maximum number of elements I can choose? It will be this, and this, right? I can choose 3 elements, right? And this is the maximum. This is not the maximum sum. This is not the actual problem you're looking at. This is just a interesting side problem that someone just asked, which I'm discussing now. Yeah. So the maximum number of elements in this case is 3, whereas 5 by 2 is in C++ at least it's 2, right, and not 3. So what is the answer? The answer is actually ceiling of n by 2, right? It's the whatever number you get, that the if it's a fraction, it's that the number above it. Yeah. If it's an even number, it's just that by 2. Otherwise, it's that by 2 plus 1. Kanak, how can it be n by 2? So for example, take 7 elements. If I have A1, A2, A6, A7, how will you pick 5 elements here? Try it out, you'll not be able to pick it 5. At max, you can pick 4 elements, which will be this A1, A3, A5, and A7. Yeah, you can't pick 5 elements amongst 7 elements without picking 2 consecutive elements. Cool. Okay, so this was a side problem. So this has nothing to do with the actual problem, right? In the actual problem, we do not care about the number of elements we choose in the valid subset. We only care about the sum of the elements that we have chosen. Yeah. So now think about that problem. So that's the actual problem. And any ideas? So okay, so some of you already gave some ideas. So let's discuss that. Naman, Kadanis doesn't do exactly this. That's kind of similar in a sense, but anyway, using Kadanis is like a hammer in a sense. We'll get to that probably later in the lecture, but no, Kadanis actually won't work for this problem. That's a slightly different DP problem. So people already gave some suggestions, so let's just discuss them one by one. So multiple of you gave the suggestion of picking alternate elements, right? So if I have A1, A1, A2, A3, A4, either choose A1, A3 or choose A2, A4, right? Because I know I can't choose both A1 and A2, so I'll pick one of them, right? I'm picking A1. If I'm picking A1, I can't pick A2, but I can pick A3. And if I'm picking A3, I can't pick A4. So A1, A3 is a natural suggestion. Similarly, if I pick A2, I can't pick A3, so I'll pick A4, right? So the answer is A1 plus A3, comma A2 plus A4. This is the suggestion which is given. Is this right? How many of you think this is right? Okay, if it's not right, give me a counter example for this. Give me an array for which this this solution will fail. Yeah. So a lot of you got guessing it correct, but give me a concrete example. Correct. 1, 2, no, 4, 2, 3, 8. Let's take this example. In this, what is this solution? This solution will say it is max of 4 plus 3, which is 7, or 2 plus 8, which is 10. And the max of this is 10. So it will say the answer is 10. But what is the actual answer for this? 4, 2, 3, 8? Correct. It's 12, right? Because I can choose 4 and 8, and I can get 4 plus 8, which is 12. Yeah. So that solution fails, right? So it need not be alternate elements. So the thinking process was kind of seems kind of natural. That is, I mean, okay, I'll start from here. Either I pick A1 or not pick 1. If I don't pick A1, I'll pick A2. So if I'm picking A1, I'm definitely not picking A2. But the thought process fails in this point that just because I'm not picking A2, so I can pick A3, but I'm not forced to pick A3, right? So I could give up not picking A3 and pick A4, right? So that's where that logic kind of fails, breaks down, right? And that's why the solution will not work. Yeah. Sid, yeah, so you can brute force. So what kind of brute force are you talking about? Even brute force is slightly not that trivial. Okay, so Naman, so Naman is talking about negative numbers. So for now, let's say all the numbers are even positive. We don't even care about negative numbers actually. It can be negative, and the solution, the final solution we'll discuss, will not change at all. But for now, let's just make our life easier and say all numbers are positive. I'm sorry, it's a bit hard to keep track with all the messages, so I'll try my best to look at all, but I'm sorry if I miss a few of them. Okay, so Himanshu has gotten it pretty down. Yeah, that Himanshu, you're absolutely right for 4 integers. But what if I have 10 integers? What if I have 20 integers? Right. Okay. Okay, so Naman has an interesting suggestion. So he's basically saying compare the first and second element and pick the maximum. Then compare the next 2 elements, pick the maximum, and so on and so forth. Does this make sense? So if I have A1, A2, A3, A4, A5, A6, I believe what he's saying is amongst A1 and A2, we know we can pick at most one of A1 and A2. So because I want to maximize my sum, what should I pick? I should pick the maximum of these 2. Right? So maybe A1 is the maximum. I pick that. And amongst A3 and A4, I know I can pick at most 1. So I'll again pick the maximum. Maybe the maximum is A3. And amongst A5, A6, maybe the maximum is A6. Right? And this is the solution. Will this work? Okay, why won't it work? Correct. Lakshit has it perfectly correct. What if amongst A3 and A4, A4 is the maximum, and amongst A5 and A6, A5 is the maximum, right? So then I'm picking A4 and picking A5, which are adjacent to each other, right? So it's not even a valid subset. So this algo might not even give a valid subset, let alone whether it being an optimal solution or not. It won't even give a valid solution. Right, so that's an issue. Okay, so Naman is giving a different solution now. So amongst 8, so he's saying amongst A1 and A2, pick the maximum. Suppose it's A2, then he is going to leave A3 and now go to A4 and A5. Right, so whichever you're picking, pick it, The next element, skip the element, because I've picked this, I know I can't pick this, right? So you'll ignore it. Then amongst the next two elements, pick the maximum. Yeah. And whichever you're picking, maybe I'm picking A4, in which case skip A5, and amongst A6 and A7, find the maximum and keep doing this. Does this algo make sense? Does everyone agree that this will give, can this ever give a invalid solution? No, this will always give a valid solution. The subset that Naman is going to choose using this protocol, using this algorithm, will always be valid. He's making sure that you never pick two consecutive elements, which is great. Yeah. So it will never be an invalid thing. So it's a very good. That's a good step. But the next question is, okay, it is a valid subset, but is it an optimal subset? Is it the subset which gives us the maximum sum? Is that true? Is it always going to give the maximum sum? Again, the same question. If not, give me a counterexample. Give me an array where this solution fails. Okay, someone gave a very, very nice example, which is 1, 2, 65, 4, and 5. Yeah. So what is this algo going to do? It's going to consider 1 and 2, the first two elements, and it's going to pick the maximum. Which is maximum? 2. So it's going to pick 2. And then it's going to skip 65, and it's going to go to 4 and 5 and pick the maximum, which is again 5. Okay. So the answer here will be 2 plus 5, which is 7. But what is the actual correct answer? For 1, 2, 65, 4, and 5, what's the actual answer? It's not 66, it's 71, right? I can pick 1, 65, and 5. Yeah. So why did he fail? Why did the thought process fail? The thought process again seemed pretty natural, right? Where did it fail? The reason it failed was when you're considering the first two elements, just because you're taking the maximum element here, you're kind of affecting the future in a very permanent way, right? So the third guy might be huge, but because I made a kind of like a local decision based on just two elements, the decision I make here is kind of screwing me up in the future by not allowing me to pick this gold mine of huge number. Yeah. Okay, I did not understand it. Yeah, so that's the main issue, right? Cool. Okay, so Diptangshu. So Diptangshu is proposing that we sort the array in descending order and then do something similar. But that's again, let me reiterate this. You can never sort this array, right? Because when you lose track of which the adjacent elements were, right? So adjacency is lost, exactly as Pratham says. You totally lose track of that. So sorting will mostly never work. So you could do something similar to sorting, but you have to keep the original array, right? Maybe create a new array, sort it, do something with it, but at the least you should definitely have the original array, right? Sure, Rhythm, so what do you do after that? So what do you do with the second array? Okay. Vidushi has a very interesting approach. Find the maximum number in the array and then in the right part of the array, again find the maximum except the adjacent and do the same in the left. Okay, this makes a lot of sense. So what, I don't know if it's he or she, what they are saying is, if I have 8 elements, find the maximum element, right? Say A5 is the maximum element. So they are going to pick A5, okay? And now that A5 is picked, A4 and A6 are definitely not pickable. Yeah, this we all agree upon, right? Now go to this half, this side, And now amongst this, pick the maximum element, right? Maybe A3 is the maximum. So pick A3. And now because I'm picking A3, A2 can't be picked, right? And now in this, find the maximum. Maybe this, so now there's only one element. So this is obviously the maximum, right? Now similarly, go to the left side and pick the max amongst all the things which are here. Maybe there are like 10 elements. Maybe there are more elements, right? Pick the maximum. Maybe A8 is the maybe A8 is the maximum, right? And because A8 is the maximum, A7 can't be picked, and stop it here, right? So let me rephrase this algo. So this is I get what you're saying, and this is very similar to a slightly different algo, which is which I think someone else also proposed, which is take the array, take the maximum element in the entire array, pick that, both its left and right, cross it out. Now in the entire array, find the second largest element, which is not picked and also not crossed out, right? So go pick that, then cross out its two neighbors and keep repeating this. Does the algo make sense? Pratish, yeah, it's not efficient, but let's not care about efficiency for now. I don't care about time limit, time complexity. I'm just worried about correctness for now. Yeah. Okay, someone is suggesting 1, 2, 10, 12, and 6. So let's see what happens. I think they're claiming it won't work in this. It won't work in this, but let's see if it works. So the maximum is 12. So I'm going to pick 12, and I'm going to cross out 10 and 6, right? And then I'm going to go to this next maximum, which is 2, and I'm going to pick this and cross out its neighbors. This 10 is already crossed out, so I don't cross it out again. And now I'm claiming that the answer is 14. But what is the actual answer in this example? In 1, 2, 10, 12, and 6? It's not 16. It's actually more than that. It's 17, right? I can pick 1, 10, and 6 to get a sum of 17, right? So they're absolutely right. This is a counterexample to the solution that we proposed, right? So why does this fail? It kind of mainly fails because when I'm picking 12 is the maximum, yes, but I'm kind of blindly picking the maximum element, but the neighbors sum itself is more than me, right? 10 plus 6 itself is greater than me, right? So I kind of fail right there. Yeah. Yeah. Okay. So Shabad has the next step in this, which is we take the neighbor sum also and print the max and take the max and consider the maximum, I think is what we are trying to say. So is it a hit and run approach? I don't know what a hit and trail approach is, but let's go with what Shabad is saying. So Shabad is basically saying, I have these numbers. Consider the largest element. Maybe the largest element is A4, but I'm not going to blindly pick A4 because I learned from my last step. The last step, yeah, Rahul, I'll get to it in a minute. So suppose the largest element is A4. I'm not going to blindly pick it because if I pick this, I know I have to cross out A3 and A5. So maybe picking A3 and A5 is larger. So I'll kind of compare A3 plus A5 and A4, right? Maybe the max amongst this is what I should be picking, right? This kind of again makes sense, right? Okay, Shivit thinks it's a perfect approach, or I don't know if they are talking about something else. Yeah, but this also seems like a very natural approach, right? But then this will also not work. It's, I think, pretty easy to come up with a counterexample. Let's think of a counterexample. Let's just take 100, 50, 51, 100, 99, 99. Yeah. So if these were my numbers, oops. Yeah. So these are my 5 numbers. This algo is going to go consider 100 and 50 and 51. 50 plus 51 is larger. So it's going to cross out 100 and pick its neighbors. Yeah. But now when I'm picking my neighbors, I have to cross out my neighbors. So the answer in this case will be just 101. But even this doesn't work. Why? The actual maximum is 99 plus 100 plus 99, which is going to give me 298. Yeah. So this also fails. So there are a lot of such approaches which fail, and one common thread amongst almost all the approaches that you're all suggesting is that they're all kind of greedy solutions, right? Either start from the left and pick the maximum here, or pick the maximum and do it, or pick my neighbors and do it. It's kind of greedy, and it's a very localized approach, right? So you're making a decision of whether to pick an element or not based on some few other numbers and not the entire array, right? And this is almost always bound to fail, at least in this setting. There are definitely settings in which such an approach does work, but in this setting it's going to fail because the decision I make here has consequences throughout the future, right? And that consequence can be made to disregard a large number for some reason, right? And so unless I'm looking at all the numbers, it's very hard for me to make a decision, right? So that's kind of the takeaway. That's kind of the reason I also went through all these approaches, all these wrong approaches, right? They all seem very natural, but kind of the takeaway is, in this problem, local approaches don't work. We need some kind of a global approach, right? And what is a global approach? I don't know anything apart from just taking all the subsets, right? So as someone suggested at the very beginning, what we can do is a brute force solution. And what is the brute force here? Look at all the subsets, right? And go look at each of those subsets, check whether it's valid or not. Checking whether a subset is valid or not is pretty easy, right? I need to just make sure that there are no consecutive elements in it. And if it is a valid subset, I'll find the sum, and I'll keep track of the maximum amongst all of this and output at the end, right? But what is the issue here? The issue is, again, the time complexity. What is the number of subsets that you have? If there are n integers, what is the number of subsets? No, it's not n factorial. Think about it a bit more. It's not n square as well. It is 2 to the n. It's 2 power n, right? Exactly. Why is this? Each element can be in the set or can be in the subset or not in the subset. There are 2 options for each element. So it's 2 into 2 into 2 into 2 n times. So it's 2 power n, right? There are multiple ways to look at this. So let's look at one other approach as well. I mean, kind of a different way of thinking of this. So this is just to look at the binary strings, right? So suppose I have these elements A1, A2 up till, let's just say, A4 and A5. What I'm going to do is, suppose I'm picking the subset A2, A5. I'm going to represent this with the binary string 0, 1, 0, 0, 1. Okay. Whichever elements I'm choosing, I'm going to make it 1, and whichever elements I'm not choosing, I'm going to put it as 0. Okay. So what does this give me? Each subset now corresponds to a binary string of length n, right? So let's just give another example. Suppose I'm considering the set A1, A2, A5. This will correspond to, what will be the binary string corresponding to this? Can you type it out? If there are 5 elements and I'm choosing the subset A1, A2, A5, correct. It's going to be 1, 1, 0, 0, 1, right? Because I'm choosing A1, I'm choosing A2, I'm not choosing A3, I'm not choosing A4, and I'm choosing A5, right? So this is going to be this is what we call characteristic vector. Characteristic vector, or another word for this is also bit mask. There are multiple names for this, right? So I'll probably just call this characteristic vector. Okay, you could also just, let's say, just give another word for it, mask. It's bit mask or mask. Okay. So why are we going to this? What is a vector? That's a good question. You don't need to worry about it. I mean, you might have, if you're in college, you might have seen vectors in high school when you did. It's like a matrix, right? It's like a 1D matrix in a sense. Yeah, cool. But that doesn't matter. Don't worry about the actual word. It's just it's not. Yeah, okay. So this vector is not the dynamic array that you see in C++. It does not refer to that vector. It's kind of like a mathematical term, which we don't need to worry about at all. Forget, just a random name, or just call it bit mask. Yeah. Don't worry about what any of them mean. It just signifies this binary string, right? But yeah, magnitude with direction. Yes, yeah. That's the physics vector. That's also not the vector I'm talking about, but it's okay. No, that's not the vector I'm talking about. I'm talking about like in matrices vector. But anyway, that doesn't matter at all. Coming back here, why are we looking at? Why are we going to this side step? I just want to kind of reiterate upon this 2 par n, right? So now all subsets can be represented as binary strings of size n, right? So it's 0, 0, 0, 0 is going to correspond to the empty subset. 1, 1, 1, 1, 1, sorry, 1, 1, 1, 1, 1 is going to correspond to the subset A1, A2, A3, A4, A5, right? So there is a bijection between the set of all subsets and the set of all binary strings of length n, right? Let me bijection between set of all subsets and set of all binary strings of length n. This makes sense, and that's the bijection is exactly what we saw. You could actually like sit and prove it's a bijection. So, but if there are any middle school students, bijection just means it's like a mapping. It's like it's a correspondence map. I take any subset, there's a corresponding binary string, and if I take a binary string, there is a corresponding subset attached to it, right? Yes, one to one and on to, exactly. Yeah, and now this is something which we are very familiar with, because this is nothing but the set of all. Okay, so can someone think of where you've seen this? Think of this in the setting of binary representations, right? So all of you, I hope all of you know decimal representation and binary representation, right? Like 5 is the decimal representation. The binary equivalent of this is going to be what? It's going to be 101, exactly. So it's 4 plus 0 into 2 plus 1. So it's 4 plus 1, which is 5, right? Yeah. So now think of it from this, keep this in your mind, and now look at this second half, set of all binary strings of length n. Can you think of some other way to look at this? So if you think of all these binary strings as binary numbers, what will be the decimal representation? What will the set correspond to then? Let's take n to be small, right? Let's take n is 2, right? So in which case, what is the set? The set of all binary strings of length 2 are 0, 0, 1, 1, 1, 0, 0, 1, right? Yeah, Naman, you're pretty close, but not exactly right, right? So these are the 4 things. So what is the decimal representation of this? Is 0. What is this? 3, exactly. This is 2, and this is 1, right? So I get this set. So the set of all binary strings of length 2, when I consider their decimal equivalent and consider that set, I get 0, 1, 2, 3. Yeah. Does this sound familiar now? So in general, what do you think it's going to be? If I take any length n and consider all the strings of length, binary strings of length n, and consider all their decimal representations, what is the set I'm going to get? That's absolutely right. Dark Knight. Yes. Yeah, Nipun, that's correct. Noble, you're making a small mistake. Shushmita, just think a bit more. You're making again a small mistake. Akash as well. So all of you are making the same small mistake. Correct. Okay. So I think most of you are getting it pretty close. It's going to be 0 to 2 power n minus 1. Right? Because what are the binary strings? It's 0, 0, 0 to 1, 1, 1, 1 n times. What does this correspond to? 1, 1, 1, 1 n times corresponds to 2 power n minus 1, because this is nothing but, if I add 1 to this number, I'm going to get 1 followed by n zeros in binary. Yeah, and that we know is 1 followed by n zeros is 2 power n, right? 1 followed by 0 zeros is 2 power 0, 1 followed by 1 0 is 2, and so on, right? So this is nothing but 2 power n minus 1, and this is 0, 0, 0, 0, and everything in between is going to be between them. That's pretty clear, right? So it's basically you're going to get everything from 0 to 2 power n minus 1, which is basically 2 power n numbers, right? And which also tells us why the number of subsets is 2 power n. I mean, this is of course a very convoluted proof to show that the number of subsets is 2 power n, but we are doing this for a reason, because we'll get back to this later in the lecture, right? Because this concept of bit mask will be pretty important. Okay, cool. So that's a kind of like a sidetrack. So now let's get back to the brute force, right? So the brute force solution is to look at all these 2 power n subsets, check whether they are valid. If they are valid, take the sum, and if the sum is and then consider the max amongst all those sums, right? So that's going to be an order n into 2 power n solution, because I need 2 power n subsets, and to find whether it's valid, I need to spend n time, and to compute the sum, I need to spend n time. So it's n 2 power n time, so it's n into 2 power n, right? That's great, but of course this is super slow, right? As we saw in the first class, 2 power n is it's literally called exponential, and it's a very slow algo, right? But what we kind of learned from so what we kind of learned is that trying to be smart and taking decisions kind of backfires, right? That's why all those wrong approaches fail to give anything. So what we are going to do is we are going to kind of give up hope, right? And say, okay, so maybe I have to do brute force, but I don't want to spend so much time, right? So what we are going to do, and that this is what DP is in its principle. DP always looks at all the possibilities, okay? Of course, the brute force looks at all possibilities. That's very clear. And what we saw till now didn't look at all the possibilities, right? So we are going to look at all the possibilities, but we're just going to do that in a slightly faster way, in a slightly smarter way. Okay. So DP is nothing but a smarter way to look at all the possible solutions. Okay. And we'll see how that works. Okay. So now we actually get to that. So the first step in any DP solution is to kind of look for sub-problems. So what do we mean by a subproblem? A subproblem is nothing but a smaller instance of the same problem. Okay, so right now the problem is I have n numbers and I need to find the just to be clear, we're going back to the main problem, right? What is the main problem? I need to find a subset with maximum sum, but the subset should be valid, right? So now the question, the when I'm initially given this number, I have n integers, and it's a lot of integers, right? It's kind of scary. I can't work if n is 100. I can't work with 100 integers. So what I'm going to say is I'm going to start out very small. I don't want to look at all the 100 integers. Let me first take one element and find the answer just for this. Then let me take two numbers, find the answer for this. Then we take the three elements, then answer for this, and so on and so forth. And hopefully I'll be able to build this larger and be able to do it fast enough such that I get to the final solution eventually. Right? So this is one common thread that you'll find in almost all DP problems, and actually literally all DP problems. Right? So we start out with some small instance and keep going larger and larger, and hopefully, and the hope is that when I want to find the answer for a larger instance, I can reuse the answer which I found for a smaller instance, right? And hopefully that will make my time faster. So very, very hand-wavy description of what we'll be doing. And here the first question is, what are these smaller instances that I'm talking about? And one natural thing is to just look at prefixes, right? So let me first look at the first element, right? Then let me consider the first two elements. Then let me consider the first three elements. Then the first four, then the first five, and then eventually, hopefully I'll get the answer for all the 6 elements. Okay, so these are going to be my 6 steps in the DP. Okay, and this is what we'll refer to as, say, DP of 1, DP of 2, DP of 3, all the way up till DP of 6. Okay, so again, let me repeat. What do I mean by DP of I? DP of I in this case is nothing but take the first I elements, right? So take A1, A2, A3 to AI, and forget about everything after that. I don't have AI plus 1, AI plus 2. I don't even have them, right? So if I'm looking at DP of 3, I'm only looking at A1, A2, A3. A4, A5, A6, I totally forget about them, right? And just taking A1, A2, A3, I asked the same question, right? Whatever the original question was, I asked the same question but for the smaller instance. Okay. So suppose my array was 5, 2, 3, 7, 8. I don't know, some random thing. Okay. DP of 3 is basically saying forget 7 and 8. Just take the first 3 elements. Totally forget 7 and 8. Okay. And if the input was just 5, 2, and 3, what is the answer? Okay. And that is what I'm going to store in DP of 3. And what is the answer? It's 8, right? It's because if my array is just 5, 2, 3, 5 plus 3 is a valid subset, and it's obvious that this is the maximum. I can't get anything larger than this. So DP of 3 is going to be 8. Okay. So what is going to be DP of, okay, maybe let's start from first. So now that you understand what DP is, what is DP of 1 in this case? DP of 1 is 5 because I have only 5. I don't have anything else. And I can only pick that, right? So DP of 1 is 5. It's pretty obvious. What is DP of 2? No, DP of 2 is not 7 because I do have 5 and 2 right now, but I can't pick both because they are consecutive elements, right? So it's not even a valid subset. So now I have to just pick the maximum amongst both of these, and of course I'm going to pick the 5. I'm going to pick 5. So DP of 2 is also 5. Yeah, and then we saw that DP of 3 is 8. Okay, and what is DP of 4? In DP of 4, I have 5, 2, 3, and 8. What is the answer for this? I don't see why people are saying 12. Suggests that your addition is bad. You can't even get 12 through any subset of this. If I'm right, it's 13, right? I'll pick 5 and 8. Yeah, 5 plus. Oh, sorry. Oh, sorry. It's 7. My bad. Thanks for pointing out. Yeah, I was being stupid. Sorry. The next element is 7. My bad. So in this case, the maximum is 5 plus 7, which is 12. Okay. Yeah. And then eventually dp of 5 is going to be I don't even know. It's probably 16. Yeah, it has to be 16, I think. Yeah. So I'll pick 5, 3, and 8, and I'll get dp of 5 is 16. Okay. But of course, I didn't tell you how to find these dp values. We just did this to tell you what dp means, what the definition of dp. This is what we mean by definition of dp, right? So take ai elements and find maximum sum subset without consecutive elements, right? This entire thing is called the definition of the dp state. Yeah, and dp of 5 in this case is going to be 16. But of course, how did I find dp of 5? I kind of just mentally did some math, looked at it, and then found. I didn't have any systematic way to find dp of 5, right? The entire concept that we're going to do now is how to do this systematically. Okay, that's the whole concept. So now let's maybe do it systematically from the first. Let's not take a concrete example. Let's say it is a1, a2, a3, a4, a5 up till an. Okay, what is dp of 1? Yes, it is a1. But you have to be careful here. If there could be negative numbers, then what will be dp of 1? It's not 0. If it's negative, then it's 0. If it's positive, then it's a1. It will be max of 0 comma a1. Yeah, it's max of 0 comma a1. I hope this makes sense, because if a1, if the first element is minus 5, then my dp of 1 is going to be 0, because the maximum sum is just the empty subset, which is kind of counterintuitive to think about it, but that's the answer, right? Because the sum of elements in an empty set is 0, whereas the sum of elements in minus 5 is minus 5. So 0 is more than minus 5. So it's max of 0 comma a1. Yeah. But then right now, let's not worry about negative numbers. Let's assume all numbers are positive. Okay. In which case dp of, so it's not going to make it, this is almost going to be the only difference that you make if it's negative. Almost everything else will be precisely the same. So let's not worry about it for now. So dp of 1, if it's positive numbers, I'm definitely going to pick a1. So it's dp of 1 is 1. What is dp of 2? It's max of a1 comma a2. Yeah, this is also pretty clear, I hope. Yeah, so it's max of 0 comma this, but then let's assume they're all positive, so you can drop the 0. So it's just max of a1 comma a2. What is dp of 3? Correct. So it's max of a1 plus a3 comma a2. Yeah. Why is this? So if I'm so I have just a1, a2, and a3. If I'm picking a2, then of course I can't pick either of a1 or a3. So that's just a2. If I'm not picking a2, I might as well pick both a1 and a3 because it's a valid subset. So it's a1 plus a3 or a2. Yeah. What is dp of 4? Yeah. So it's max of a1 plus a3 or a2 plus a4 or a1 plus a4. This is also important. Yeah. This is just the example we saw earlier. Yeah. And now try dp of 5. You'll see that even dp of 5 becomes slightly complicated. Yeah. So till now it was pretty easy, but as you go larger and larger, it's simply because the number of subsets that you need to consider is large. So all these types of manual effort will be totally pointless. Okay. Yeah, so yeah, there are no negative numbers. So what didn't you get to with? So dp of 4 is just, if I have a1, a2, a3, a4, I either pick a1 and a4 or a2 or a4 or a1 and a4. You can see that nothing else will be a valid. These are the only valid subsets. Yeah, cool. But of course, all this is going to be, just doing this manually is totally useless. Now the question is, how do I find dp of I for any generic I? Okay. Yeah. So now we want to find a very systematic approach. So what is dp of I? Let's again look at the definition. I have a1, a2, a3, ai minus 2, ai minus 1 and ai. I want to compute dp of I, but I want to do this in a systematic way. So what do I know? So if I'm computing a dp of I, it means that all of dp of 1, dp of 2, all the way up till dp of I minus 1, all of these terms I've already computed. Okay. Because I'm computing them one by one, right? First I find, because I'm starting with a small instance, then a larger, then a larger, then a larger. So all the dp's before me, I've computed all of them and I've stored it in an array, in a dp array, right? So now to compute dp of I of course don't want to go and look at all the subsets of this, because that's going to take 2 power I time, right? I don't want to spend so much time. But I still want to kind of consider all the subsets. But I want to do it in a smarter way and somehow reuse the dp values that I've already computed. Yes? So how exactly do we do this? This is the main question. Okay. And the first thing that we do, the first thought process I would say is, what are the things we know so far? We know about these guys, but notice that none of these dp values ever look at ai. Yeah. So ai has been kind of ignored in all these dp values. Correct? I hope this makes sense. None of these values, so dp I minus 1 is kind of the largest instance I've seen so far, and even that looks at only the first I minus 1 values. They don't look at ai, right? But then I have to look at ai as well. So what I'm going to do is I'm going to focus on ai, because none of the others have done it. So I have lots of people, they've done some work. I want to take their help, but then amongst the elements that I have to look at, none of them have worked on the last element. So I'm going to put in my work into the last element, and for the rest I'm going to use their help, right? So this is why this is kind of the main thought process behind this. So what am I going to do? I'm going to go look at ai and ask, what are you going to do, right? So in any valid subset, ai is either present or not present, right? And this is the main distinction I'm going to make. So now we'll get to the, so just keep this in your mind. But how do we use that exactly? So before getting to that, let's look at kind of a visual representation of what we are doing. Okay. So the way I like to, so there are lots of ways to do this. This is definitely a very personal take on this. The way I like to imagine this, at least for the easy problems, is to visualize every dp as a bag which has all the valid subsets of the instance that it considers. Okay, so dp of 1 will consist of a bag which has the empty subset and the subset a1. Okay, dp2, when I'm looking at dp2, I'll be considering a bag which has the empty subset, the subset containing just a1, subset containing just a2. It will not have the subset containing a1 and a2 because it's not valid, right? My bag contains only the valid subsets, right? dp of 3, let's say this is dp of 3. When I'm looking at dp of 3, I'll be considering the bag which has the empty subset a1, a2, a3 and a1 comma A3, right? So now I hope it's clear what I'm talking about. So these are all the valid subsets of the first three elements, and dp of 3 is nothing but the maximum sum amongst all these guys. So it's max of 0, this empty subset is 0, a1, a2, a3 and a1 plus a3, right? This is the actual max, this is actual dp3, but then because these numbers are positive, I don't need to consider the empty subset. I don't need to consider a1 because a1 is less than equal to a1 plus a3, and I don't need to consider a3 because a3 is less equal a1 plus a3. So I end up considering only this and this, and that is why we got this equation, right? This equation is actually a kind of a clever equation. The brute force equation would have been max of 0, comma a1, comma a2, comma a3, comma a1 plus a3, right? Which is what I'm doing here. I'm not being smart. I'm not crossing these things over. I'm considering all of them and putting it into a bag. Okay. So dp of I in general is a bag. When I'm looking at dp of I, I'm going to consider a bag which has, maybe I should draw a larger bag. Yeah. This bag has all the valid subsets of a1, a2 to ai. Okay. So why does this help us? It helps us in getting to this part, right? So now let's go back and ask what we did with ai, right? And we decided that it's either I'm going to pick ai or I'm not going to pick ai. My valid subset can either have ai or it cannot have ai. It's an obvious dichotomy, right? A set can have ai or it can't have ai. So now let's come back to this set, this bag. This bag has all the valid subsets. Now I'm going to break it down into two bags. Okay. And in the first bag, I'm going to put all the valid subsets which don't contain ai. And the second bag, I'm going to put all the subsets which definitely contain ai. So I hope people know what this symbol means. This means there has or there exists. So there exists ai in all the subsets is what I mean by this. Okay. So in particular, so this is going to have subsets like, so if a1, if I is say 5, right? So then this is going to have some a1, a3, a2, comma a4, just a3, just a4, empty subset. All these valid subsets which don't contain a5 will be in the first half of the bag, first sub bag, right? And the second sub bag will have all those valid subsets which definitely have a5. So things like just a5, a3, comma a5, a2, comma a5, a1, a3, a5. Any valid subset which has an a5 in it will be put into the second bag, right? So now do you see that these two bags kind of like partition the large bag into two halves, things which don't contain ai, things which contain ai. Okay. And now the point is, consider this smaller bag, the first half, things which don't contain ai. Do you see that this bag is exactly the bag that we considered when we were looking at dp of I minus 1, exactly, for 4, right? Because what is this? These just contain all the valid subsets of a1 to ai which don't contain ai, right? So if it doesn't contain ai, it just means it's a subset of a1 to ai minus 1, right? So it's just all valid subsets of a1 to ai minus 1, which is exactly what we considered when we were looking at dp I minus 1, right? And that's exactly, so this bag is nothing but the dp I minus 1 bag. And in that bag, what is the maximum sum? We had already calculated it, and that was nothing but dp I minus 1. Yeah. So the maximum amongst all the elements here is just dp of I minus 1. Does it make sense? All I'm saying is we have this huge bag. We want to find the maximum of all the maximum sum amongst all the subsets here. Now we broke it into two halves, and I'm saying the first half, the maximum sum amongst all those valid subsets is just dpi minus 1. Yeah. Now let's go to the second half, right? So second half has things like a1, comma a3, comma a5. Sorry. Right? Lots of such things. Now, the important point is that all these valid subsets have one element in common, which is a5, right? So what we're going to do is we're going to take a5 away from it. Okay. So we're going to take this bag and convert it into a5 plus another bag, right? We're going to remove a5 from each of these because every element in this has a5 in it, right? So I'm going to pluck out a5 from each of them. So this subset, which has only a5, will now become an empty subset. Okay. The subset which was a3 comma a5 will now become just a3 because a5 has been plucked out and it's common out here, right? a2 comma a5 will just become a2. a1, a3, a5 will become a1 comma a3. Yeah, there are many more such subsets. I'm not looking at all of them. I'm just looking at these four subsets, which are all part of this bag. And now I'm picking out a5 from all of them. Why am I picking out a5? Because I know it's there in that. So a5 is going to definitely be there in the sum. It's going to be a5 plus something, something, something. Right? We are only interested in the sum of all the elements in these bags, right? And each of the subsets in this bag. So I just take out common, right? Because what is the eventual goal? The eventual goal is to find the subset whose sum is maximum. And if I know there is all of them have a5, I can pick it out and then take the maximum and just add a5. I'm going to get the maximum sum, right? That's the principle behind what we are doing. So I pluck out a5 and I have this subset now. And if I can find the maximum subset in this, I'll just add a5 to it and I'll get the maximum in this bag. Yeah. So I've just transformed this bag into another bag, but after removing a5. I hope this makes sense. Yeah. So now the question is, what is the maximum sum subset in this new bag? Let's try to do it along the same principles, right? So I had a1, a2 to up till a5. a5 was chosen, so I've removed a5. So now this is going to be subsets of a1 to a4. That is subsets of a1 to ai minus 1. Yeah. Why is it not that? It is, right. So all these elements, all these subsets are definitely going to be valid subsets of a1, a2 to ai minus 1, right? All of them are valid, definitely, and they don't have ai, that is a5. So they're all between a1 to a4, right? So can I just say it's dp I minus 1? So can I just say it's a5 plus dp of 4? Yeah. So many of you have got the error in this. I can't do that, right? Why can't I do it? Because in dp of 4, in the bag corresponding to dp of 4, which was this, I would have had elements like a2 comma a4, right? a2 comma a4 is a valid subset for the first 4 elements. But if I take a2 a4 and then I add a5, I get a2 a4 a5, which is no longer a valid subset, right? a2 a4 is a valid subset when I'm looking at the first 4 elements. So in dp4 this will be there. But now if I take that, suppose this was the maximum of dp4, and if I plug in a5 at the end, this is no longer valid, right? Because a4 and a5 are adjacent, and that's not allowed. Yeah. So yes, it is true that all these elements are valid subsets of a1, a2 to ai minus 1, but it's the other way around is not true. Yeah. in particular, do you see that because A5 was chosen here, right? So these were all valid subsets which have A5. So because A5 is there, A4 was definitely not there, right? In general, talking about it in general terms, this bag has all the subsets which definitely contain AI, and because it's valid, AI minus 1 is also not present. So now when I took out AI is not there and AI minus 1 is not there, which means these are subsets of A1 to AI minus 2, right? And which brings us to, and the max of that would be dp of I minus 2. Yes. And now let's look at the other way around. Yes, so all these elements will be in the dp I minus 2 bag, but is it exactly equal? That is also true, right? Because let's take any element, any valid subset of A1 to AI minus 2. If I plug in A5 at the AI at the end, it still remains a valid subset because AI minus 1 is not chosen, right? So take any valid subset of A1, A2 to AI minus 2, and if I add AI to it, I claim I'm going to get a valid subset of A1, A2 to AI. Yes. But if this was AI minus 1, this is no longer true. That was no longer true because AI minus 1 could have been chosen, and if I add AI, I get consecutive. But here, any valid subset of this will not contain AI minus 1. So when I put in AI at the end, I'm not bringing in any adjacency illegal moves, right? What is illegal? I mean, a subset becomes invalid only when two consecutive elements are chosen, right? But that can never happen here because AI minus 1 is there in between, right? AI minus 2 is there, then I have AI minus 1, which will definitely not be there, and then I have AI which I'm choosing, right? So when I'm putting in AI into this, I'm not causing any adjacency I'm not causing any extra adjacency. So if this was valid, this will still remain valid. Yeah, and that's the whole point. So this bag is exactly the bag corresponding to dpi minus 2, right? Because we've shown both way direction. Anything here is in dpi minus 2, and anything in dpi minus 2 will be, if I plug in AI, will be in this thing, so it's there here as well. Yeah, so it's kind of like a bijection in a sense. So we show that this bag is exactly the bag corresponding to dpi minus 2, and so the maximum here is nothing but dpi minus 2, and so the maximum here is AI plus dp of I minus 2. Okay, I hope that makes sense. So what are we basically saying? At the end of all this, our claim is nothing but dp of I is max of dp of I minus 1 comma AI plus dp of I minus 2. Yeah, this is when the valid, this is the maximum amongst all the valid subsets which don't contain AI, and this is the maximum amongst all the valid subsets which definitely contain AI. And for dp of I just have to take the maximum amongst both the bags. I found the max amongst everything here, and I found the max amongst everything here. So the maximum in the whole bag is just the max of the two maximums. So it's max of the two maximums, which is just this. Okay. So this is all there is to this problem. So this is the dp recurrence. This is called the dp recurrence formula. Okay. So what we have here is dp of I depends on dp of I minus 1 and dp of I minus 2 and the input AI definitely. Yes. So what did we saw? We initially saw the base cases, right? So we have dp of 1 was A1, dp of 2 also we found, which was max of a1 comma a2. And now for dp of 3, we don't need to do whatever we did. We can just use this. So it will be max of dp of I minus 1, which is dp of 2, comma ai, which is a3, plus dp of I minus 1, sorry, I minus 2, which is dp of 1, which is just a1, which is a1, right? So it's max of a1 plus a3, comma dp of 2, which is max of a1 comma a2. But I mean, I can kind of ignore this a1 because this a1 is here as well, right? But dp doesn't ignore. dp will, when we did it, we kind of ignored it, but dp kind of does everything. It looks at all the problems, right? So this is dp of 3, and similarly dp of 4 would be max of dp of 3, comma a4 plus dp of 2, and so on and so forth. Then now that I know dp3 and dp4, I'll find dp5. Then I'll find dp6 using dp5 and dp4. I'll find dp7 using dp6 and dp5, all the way up till dp of n. And the final answer is going to be dp of n, right? Because I have all the integers, and what is the maximum thing I can get? That's the original problem that we had. Yeah. So that's basically it for this problem. So a code for this would be just first take input and then find create an array of size n, or size n plus 1 if you want to be one based indexing. Then populate the base cases, so dp1 and dp2, do it by hand, and then write a for loop from 3 to n, and dp of I, write this equation. And you know that whenever I'm going to compute dp of I would have already computed dpi minus 1 and dpi minus 2. Yes. And because we already know this, I can compute dp of I, and at the end just do cout or print dp of n, and that's it. So the time complexity for this is just order n, because it's just one for loop, right? And the time taken to compute one single element, we call this a dp state, right? So dp of I is one state. To compute this, it's just constant time. It's just two terms, and we want to take the maximum of both these, which is just constant time, right? So, and there are n states to compute, dp1, dp2, there are n different dp states. Each of them I spend like constant time. So total time is just order n, right? So the time complexity would be order of n. And what is the space complexity? Space complexity is also order n, because one, I need an array to store the input, and then I also need a dp array, a second dp array. Yeah. So I'll store that and keep it. So it's order in space and order in time complexity. Cool. Okay, so let me look at some questions. Okay, so I think most of these are old. Yeah, you can definitely do this using recursion as well, which is just top down. But then there'll be recursion and not dp. You can definitely do it. No question. So base case will just be inside the recursion, and it will definitely work. So recursion and dp are very often interchangeable. Many things. So dp kind of relies on recursion in a sense. It's just in a sense a cleaner way to do it. And there are some complex problems which doing with recursion is going to be pretty hard. So we go for dp. It's just it's cleaner to think of the order in which you need to do things, and some optimizations which work out easier in dp. Yeah. Corner cases, no, there are no corner cases, except so base cases are kind of like a corner case in dp. You'll usually not have many corner cases when you do a dp approach. So you just need to keep track of, like, when n is very small, what is going to be the answer, like 0 or 1, which anyway you're doing using your base cases, so you don't need to worry about it. Yeah, so binary strings, we'll come to that. So I hope this makes sense. Okay, so Madhu has a very interesting question, which is, can we print the elements of the subset using this method? Yes, you can. So what you would do for that would be, you go to dp of n and check whether dp of, so okay, so maybe some of you didn't hear. So the question that they asked was, now using this approach we just found what is the sum of the maximum sum of the subset, but how do we find the actual subset, right? How do we find it's a1 plus a3 plus a5, right? And that's not very obvious. So this is actually slightly more I mean, usually problems don't ask for it because it's easy to do it. It's just slightly more coding. It's kind of like dirty coding. People like, I personally never like it, and I think that's the case with most people because it's conceptually mostly the same, except that it's slightly more dirty. But anyway, the way to do it is just to keep track. Like, so let's look at this equation, right? Yeah. So in this equation, dp of I, if this was the maximum, it means that I'm not picking ai, right? But whether if this is the maximum, it means I'm picking ai. So all I'll do is I'll go to dp of n. I'll check whether dp of n came from dp of n minus 1 or dp of n minus an plus dp of n minus 1 and n minus 2. If it came from dp of n minus 1, it means I'm not picking an. So I'll just go to dp of n minus 1 and see where you come from. But if it did an plus dp of n minus 2, I know an is in the subset, so I'll add an to the subset and then go ask dp of n minus 2 as to what your subset is. And then I keep doing this iteratively. Yeah. This is the almost all DP problems is how, if you want to get a subset or the actual instance behind the maximum or minimum or something, this is the trick you'll always use. Cool. Will I implement it? I probably won't spend time implementing it. I'll give you some practice problems which you can try later. I'll also give you code which you can look up after this. We'll put it up on the Discord server. Yeah. So cool. So let's move on to the next problem. So the next problem I wanted to do was tiling problem. So, oops. So this is a family of problems. We look at one of the simplest problems. Yeah, and that is, say you have a floor of size 2 cross n, okay, and you want to tile these elements, tile the floor, and the tiles you have are basically what we call dominoes, okay, this or this. And the question is, how many ways are there to tile this floor using either this vertical or a horizontal floor? How many different ways can we tile? What are the constraints? The constraints are that you can't, no two tiles can overlap. Okay, so I can't have something like this. These two tiles are like overlapping with each other, right? That can't happen. And a tile can't go outside a floor. And every cell, so each of this is a cell, right? And each cell should be covered by a tile. Okay, these are the main constraints. So let's maybe look at an example. So when say n equal to 2, so you have a floor like this. What are the different ways to do this? How many ways are there to do this? Correct, it's 2 ways and not 4 ways. So one way is to do this. Use 2 vertical tiles or use 2 horizontal tiles. There are no other ways. Okay, so these are the 2 ways in which you can tile a 2 cross 2 floor. But what about n equal to 3? Okay, my drawing is super bad. Can you please explain the problem again? Yeah, sure. So you have a 2 cross n floor like this, and I want to tile it The tiles I have are of two types. This is a vertical tile and this is a horizontal tile. It's only two length each. How many different ways are there to tile this? And the constraints are that no two tiles can overlap, and every cell should be tiled, and a tile can't go outside a floor. So I can't keep like a I can't do this. I can't place a tile like this because it's going away out of the floor, right? It can't go out of the floor. And similarly, I can't place one tile like this and say another tile like this, right? Because these two tiles are overlapping. This is also not allowed. Yeah. So now coming back here, for n equal to 2, these are the two ways of tiling. So either two vertical or two horizontal. So it's 1 and 2 ways. So the answer for 2 is 2 ways. There are 2 ways. Answer is 2. Permutations of tiles are not different. I mean, all the tiles are identical to each other, if that's what you mean. Yeah. So let's look at just the different ways in which you can tile this. For 3, it's 3. You're right. The 3 ways would be, this is one way. This is another way. This is another way. Yeah. So I have 1, 2 and 3 different ways. You can see that there are no other ways in which you can tile. The floor is, it's a floor or rectangle. I mean, the floor is always 2 cross n, width 2 and length n. That's always the case. Yeah. So now how do we solve this problem? So for obviously for n and 2 and 3, it's kind of easy, and you will see that as you go for larger floors, it's going to become harder and harder. Right. So we'll see. So how do we go about solving this? So I maybe because we are kind of like running late, so let me just no, for n equal to 4, it's actually not 6. I think you're making a small mistake. I'm not sure where. Maybe try again. Yeah, it's actually 5. Okay. So let's go with our same approach, right? I have a 2 cross n. And our DP definition is going to be pretty much the same. In this case, what will be our sub problem? We don't have any integers, so I can't say first I integers. Instead, I'm going to say, instead of 2 cross n, I'm going to look at 2 cross I, right? So what is the thought process again? So the original problem is large, but I'm looking at small instances and building up from there. So the smallest instance is just a small floor, and then a slightly larger floor, and then a larger floor, and then a larger floor. So right. So dp of 1 will be, if I just have a 2 cross 1 floor, if the floor itself is like this, there's only one way to tile it, right? I can just do this. I can't do anything else. So the dp of 1 will be 1. dp of 2, as we saw here, the number of ways to tile a 2 cross 2 floor is 2 ways. So dp of 2 will be 2. dp of 3 will be slightly larger floor, 2 cross 3, and as we saw, the answer is 3. Right. So now, in general, for dp of I don't have 2 cross n. I have 2 cross I. Yeah. So now, how do we what do we do here? How do I compute dp of I using the previously computed dp values? So I know dp of 1, dp of 2 up till dp of I minus 1. How do I compute dp of I? And what is the thought process again? The previous dps looked at the previous columns, but none of them looked at the ith column. So let me go and focus my efforts on the last column, right? And in the previous problem, the question was, am I taking this in a subset or not? But there's no concept of taking or not taking here, right? Because every cell has to be tiled. The question is, how is it tiled, right? So the question here is, how is this last column tiled? And in particular, let's just focus on the last top right cell. Okay, this top right cell has to be tiled somehow. It has to be covered by some tile. What is the tile which is covering it? Okay. So again, going back to kind of the bag intuition, bag visualization, dp of I is this bag containing all the possible tilings, right? And dp of I is nothing but the number of subsets in this. Okay. And what we are going to ask here is, how is this cell tiled? And the answer for that is, it can be tiled either using this or using this, right? So it can be like this. That is one possible way, or maybe this is tiled using this. And these are the only two possible ways in which the top right cell can be tiled. Right. And that is what we are going to break our bag into. Is the top right corner tiled using a vertical tile, or is it tiled using a horizontal tile, right? And this is how the bag is split. So let's look at the vertical tile. So if this thing is being tiled using this blue vertical tile, do you see that now I can just ignore the last column and just find the number of ways of tiling the first I-1 columns, which is nothing but dp of I-1. Yeah. So it's this contains all the valid tilings in which the last tile is a vertical, the top right thing is a vertical tile. So let me take that out common from all of them. What I'll be left out with is a bag containing all valid tilings of 2 cross I-1, right? And the number of ways there is nothing but dp of I-1. Yeah. And the other way is, the top right corner is tiled using this. This is the top right corner. And if this is the case, do you see that this should also be another horizontal tile here, because there is no way I can tile this using a vertical tile. So the beneath that will be another horizontal tile, right? So everything here will end with 2 horizontal tiles at the end towards the rightmost, and I'll take all of them common. Once I take all of them common, what I'll be left with is all the valid tilings of 2 cross I-2, which is, and the number of ways of doing that I know is dp of I-2. Yeah. So finally, so the total number of things in this whole thing is the number of elements here plus number of elements here. It's not max anymore because we're counting, not finding the maximum of anything, right? Just counting. So dp of I is nothing but dp of I-1 plus dp of I-2. And this is all. So we have dp1, dp2. dp3 is nothing but dp1 plus dp2, which is 3. dp4 is nothing but 2 plus 3, which is 5. And I'm sure all of you recognize what this is. This is nothing but the Fibonacci sequence. Yeah, precisely. It's exactly the Fibonacci sequence. Fibonacci sequence generally starts with a 1 at the beginning, but yeah, it's the same thing, right? And that's it. So this again is just order n, right? Because we have an array, you first array of size n, so space complexity is also n. Do the base cases, do dp of 1 equal to 1 and dp of 2 equal to 2, and then write a for loop from I equal to 3 to n, and at each point compute dp of I is dp of I-1 plus dp of I-2. It's as simple as that. Yeah, and then you get eventually dp of n, you output. Great. Cool. So that is just the this is kind of the simplest tiling problem. There are lots of variants after this, which we'll not go into. I'll try to do different problems now. So cool. So let's move on to a slightly harder problem. This is called LIS. Okay. This is longest increasing subsequence. Okay. What is this problem? This problem is you're given an array which is A1, A2, A3, A4, AN. You want to find a subsequence of this, right? So what is the difference between a subset and a subsequence? A subset is kind of like an orderless subset. You don't care about the order so much, but in a subsequence you care about the order as well, right? So a subsequence, so in this A2, A3, A5 is a subsequence. It is also a subset, but say A3, A2, A5 is not a subsequence. A3, A2, A5 is not a subsequence because the subsequence should be in the same order as it is in the original sequence. Okay. Whereas A3, A2, A5 is a subset because sets don't care about ordering. That's a difference. That's like a terminology difference which you should be careful about because a lot of problems use these terms. So understand what these terms mean. So now what we're looking for is a subsequence, and that subsequence should be increasing. What does it mean by increasing? It should be ascending, right? So if A3 is less equal A4 is less equal say A7, then A3, A4, A7 is an increasing subsequence of the given array. Okay? It doesn't have to be contiguous. It can skip elements. There is no such constraint that it should be contiguous. Okay? If it's contiguous, the term which we'll use is a subsegment or a subarray. That is the term which usually means contiguous. But when it's a subsequence, it doesn't need to be contiguous. Okay. So given a sequence or given an array, there will be lots of increasing subsequence, and what you want is the longest such increasing subsequence. Okay, so let's take an example. Say I have 5, 1, 3, 7, 4, I don't know, 6. Okay, so in this 5 and 7 form an increasing subsequence. Okay, but 5, 7, 6 don't form an increasing subsequence because it's increasing and then decreasing. That's not allowed. 1, 3, 7 is an increasing subsequence. But what is the longest increasing subsequence? The longest increasing subsequence would be 1, 3, 4, 6. Yeah, exactly. So all of you got it right. So it's 1, 3, 4, 6. The length is 4. Okay. So this is the problem. I hope the problem is clear now. Given any array or a given any sequence, you want to find the length of the longest increasing subsequence. Let's assume all numbers are distinct. If it's not distinct, it doesn't change anything. I mean, if they're equal, you can either look at strictly increasing, or you might be fine with 1, 4. 4 also is fine. All these variants don't make much of a difference conceptually. It's just some very small tinkering that you need to do to get the answer for these. Okay. So for now, let's just make life easy and say all the numbers are distinct. All the numbers given in the input itself are distinct, so we don't need to worry about strictly increasing and monotonically increasing. So cool. So given this problem, so now again, let's say we do some greedy approaches, we don't get anything, so then we give up hope and then come to DP, and we apply the usual DP. We kind of blindly say, what is the usual thing we do? DP of I is the first I elements, what is the answer, right? That's the first step, kind of the first thing that we always do. So we say, okay, DP of 1 is, if I have just the first element, what is the answer? What is the answer for this? It's not 5, right? Because what is the definition of DP of I? The DP of I is the maximum length of the increasing subsequence. So it's 1. Right? I'll pick A1. So it's 1. What is DP of 2? Yeah, so with what does it depend on? So a lot of you are saying 1. It need not be the case, right? Because I have A1 and A2. If A1 is less than A2, then I can pick both A1 and A2, right? If I have, in this case, I can't pick 5 and 1. But if it was 1, 5, 3, 7, 4, 6, then I could pick 1 and 5, right? So in which case the answer would be 2. If not, I can pick either 5 or 1, right? So DP of 2 is basically, if A1 is less than A2, then DP of 2 is 2, else it is 1. It will be 1 or 2, depending on whether A1 is less than A2 or A2 is less than A1. If A1 is less than A2, then I can pick both of them and it will be increasing. So it's an increasing subsequence. So the answer is 2. But if A1 is greater than A2, then I can't pick both A1 and A2 because it forms a decreasing subsequence and I can't do that. So I need to pick either A1 or A2. In either case, the length is 1. So in that, if A1 is greater than A2, the length of the largest increasing subsequence will be 1. Okay, great. Similarly, DP3 also I can do some manual work and find it, but we don't want to do that manual work. We want to go to the general formula, right? So general formula is dp of I. What is dp of I? And when we want to do dp of I, I assume I know dp of 1, 2, 2, dp I minus 1 I know. So I have A1, A2, A3, AI minus 1, AI, right? So great. So now, what is the next step in the DP process that we saw? All the other DPs look at the first I minus 1 elements, but I need to look at all the I elements. So I'm going to go focus on the last element because none of the others have done it. So I'm going to focus on the last element. So I'm going to go and focus on AI. And what is the natural bifurcation? Either AI is part of my increasing subsequence or it is not a part of my increasing subsequence. So I have this bag which contains my bag contains all the increasing. So what is this bag? It contains all the increasing subsequences of A1 to AI, right? These are all like, now I hope you see the common process that we are following, right? When I look at dp of I, I consider a bag which has all the valid potential answers, right? And actual dp of I will be the length of the longest valid increasing subsequence. So this contains all the increasing subsequences, but now I'm breaking it into 2 bags. This has all increasing subsequences which don't contain AI, right? And this contains all increasing subsequences which definitely contain AI. Yeah. And now what happens with this bag? This bag has all the increasing subsequences which don't have AI. And is it obvious that that is just all increasing subsequences of A1 to AI minus 1, and which is nothing but dp I minus 1, right? So the maximum length here, this bag is actually identical to the bag we saw in dp I minus 1. So the maximum length here is nothing but dp of I minus 1. Yeah. But now when we come to the second bag, this is where the fun begins. Now, okay, I know AI definitely has to be chosen. Great. So it's like 1 plus. I can add 1. But now, what do you do? So now what I would ideally like to say is I want to take dp I minus 1 and do a plus 1. But will that work? Can I say that the longest here is 1 plus dp of I minus 1? Why not, Shayan, Akash? Where am I going wrong? Correct. So dp of I minus 1 could have picked a sequence, say A2, A3, say I is 10, right? Say dp of 9 could have selected A2, A4, A2, A3, A7 is say the longest in dp of I minus 1, right? And maybe A3 is some 100, whereas AI is, I don't know, 50, right? So now I can't take this 50 and shove it at the end of this increasing subsequence earlier, because then I get maybe A2 was 5, then 30, then 100, and then I cut to AI is 50, which comes down, right? So that doesn't work out, right? So I can't just blindly take any increasing subsequence earlier and shove in AI at the end, because I need to make sure that the previous increasing subsequence ended at a value which is less than AI. Yeah. But then how do I know this? So I see one thing that many people are suggesting is consider AI minus 1 and AI. But that also doesn't help, right? I mean, AI minus 1 could be less than AI, right? Consider the sequence 1, 2, 3, 4, 2, 3. Yeah. Let's actually just consider this sequence. What is dp of 5 for this? In this 6 element subsequence, what is dp of 5? That is, if I consider only the first 5 elements, what is the max longest length of the longest increasing subsequence? It's 4, right? It's 1, 2, 3, 4. Yeah, exactly. But now what is dp of 6? Even though 2 is less than 3, I can't say it's 1 plus dp of I minus 1, right? It is still 4. It is not 5. I can't take 1, 2, 3, 4 and shove in 3 at the end, even though 2 is less than 3, right? So I hope that, so many of you are suggesting this. So it's not enough to just compare ai minus 1 and ai, because dp of I minus 1 might not have ended at ai. It might have ended anywhere. I don't know where it ended, right? So what I need to compare with is what was the ending element of the increasing subsequence, right? So this kind of brings us to the next point, that maybe, okay, so maybe in dp of I shouldn't just store the length of the longest increasing subsequence. Maybe I should also store the last value. Yeah, and then I could compare. But then this goes into more complications, because there could be multiple increasing subsequences of the same length. So then which last element do I pick, right? So this is a huge issue which comes up, and it's not easy to solve that. Okay, there are a lot more complications in this. I'll not get into what exactly. So typically, just keep this as a rule of thumb, that in DP, usually keeping track of some property of the maximum or the optimal solution in one DP state, taking a property of it and keeping it and trying to maintain that, usually will not work out. Okay, if it turns out that you have to do something like that, then you probably have to go and tweak your DP itself to put that property in the DP. Okay, this is what it usually boils down to. So what we'll come to here is, I can't find the answer, right? Because I don't know what the increasing subsequence ended at. So now I'm at a kind of like a standstill. I don't know what to do, right? So what we are going to do is rather go back to the definition of the DP, okay, and tweak the definition of the DP itself. So basically, I took the most natural definition of DP. I did everything that we did earlier at the same process I followed, and we ended up at a place where we are not able to go further. We are not able to find the maximum of the second bag. And why aren't we able to find it? Because we don't know where the increasing subsequence ended, right? When I just consider DP of I minus 1, it could have ended wherever, and I have no idea about that, right? So that is the bottleneck, right? And what we need to do now is we have to go tweak the definition of the DP to kind of inculcate this bottleneck as part of the DP definition itself, right? So, with why don't we know where it ended? Yeah, so basically in this example, in DP of 5 is 4. 4 is just the length, right? So maybe this was 11, 12, 13 and 14. 4 is just the length. I don't know where exactly it ended, right? I'm not keeping track of that. The 4 was not the number, it was rather the number of elements. Maybe my example is, maybe here I should have like say another 3, and then these are DP of 6 and DP of 7, right? You can tweak these and get it. Yeah, so that's the main issue. So now what we are going to do is we are going to go back to the definition of DP and say DP of I, I'm going to put in extra constraints and say I'm not going to look at all the valid increasing subsequences of A1 to AI, but what do I want? I basically want a handle on where these increasing subsequences end, right? That is where I was failing. I didn't know where they ended. So I'm going to go back to the DP definition and say DP of I is not just any increasing subsequence in A1 to AI, but rather I'm going to only take those increasing subsequences which end at AI. Okay, I'm adding an extra constraint and saying, okay, yes, there are a lot of increasing subsequences in A1 to AI, but I'm going to only consider those increasing subsequences which definitely end at AI. Okay, so I'm looking at a subset of the original things and saying, now amongst these increasing subsequences, what is the longest? Okay, so let me repeat what I said. So earlier, let me just write down both the DP definitions. Old DP definition was length of longest increasing subsequence in A1, A2 to AI. Yeah, DP of I was nothing but the length of the longest increasing subsequence in A1, A2 to AI, right? But now we are going to tweak this, and the new DP definition is going to be DP of I is the same. I'm going to write all the exact same thing, blah, 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 with an extra constraint by saying, and this longest increasing subsequence should also end at AI. Okay, I'm just putting in an extra constraint and saying I only consider those increasing subsequences which end at AI, and amongst those I want to find the longest. Okay, it's a bit counterintuitive at first, but the reason we are tweaking this is because we want a handle on where subsequences end, right? Because that is where we failed. That's why we come and tweak this definition to this. Okay, so now let's do the same process again with this new definition and see if it goes through. So now what is DP of 1? DP of 1 is again 1, right? I have A1 and I'm just going to pick A1. It ends at A1, so great, no issues. Yeah. What is DP of 2? DP of 2 again depends, right? If I have 2, 5, DP of 2 is going to be 2, right? It's the same thing. This doesn't change. If A1 is less than A2, then DP of 2 is 2 because I'll pick both A1 and A2. It ends at A2. Else, it is just 1. I have to, if it was not 2, 5, instead of that, if it was 5, 2, I have to only pick 2, right? Earlier, I could have picked 5 as well. But now I have this constraint that it should end at AI, so I can only pick the last element, the second element. Yeah. But either way, the DP length is just 1, so it's just 1. Okay. So DP of 3 would be if I have A1, A2, A3. The different things I would consider is if A1 is less than A2 is less than A3, then it's 3. Right. If not, if A1 is less than A3, it's 2. Or if A2 is less than A3, then it's 2. Or if both A1 and A2 are greater than A3, the answer is 1 and I can pick only A3, right? So again, it's 1 or 2 or 3. The DP value will be 1 or 2 or 3 depending on which of these conditions is true. But I'll not write all of them because we are anyway looking at a general solution. So in general, when I come to DP of I, how do I compute DP of I? So again, what do we have? We have A1, A2, yeah. So now again we have this bag. Which has all the, right now it has all the increasing subsequences which end at AI, right? I have this extra condition as well. So AI is definitely picked. There is no doubt about this, right? AI is definitely picked. So now what do I do? So I usually go and focus on AI and figure out what to do with it, and that's how we usually divide our bag into multiple bags, right? But no, we can't do that because AI is definitely there. So what do I divide it into? So instead, what we're going to ask is, I know AI is the last element of my increasing sequence. What was the previous element? What is the last but one element? Okay, and that is the question I ask. Okay. Is it clear? So that could be the previous element could have been AI minus 1. It could have been AA minus 2, it could have been AA minus 3, or it could have been A3 or A2 or A1. It could have been any of these. Yes. So yeah, so an example would be, say I have, okay, let's just look at this concrete and let me just try to explain here. So I'm right now looking at all increasing subsequences which end at AI. Yeah. Sure, it ends at AI. Say, so maybe I have one increasing subsequence which is A2, A4, say I is 10. Yeah. So A2, A4, A7, A10. If A2 is less than A4, which is less than A7 is less than A10, then this would be an increasing subsequence. It has to end at 10. So it's a valid increasing subsequence. But now I'm basically asking, which was the last element is A10, that's compulsory. Which was the previous element? In this case, previous element is A7, right? I could have had another increasing subsequence, say A3 and A10. Maybe it's just 2. Maybe A3 is less than A10. So A3 and A10 is a valid increasing subsequence. In this case, the last element would be A3. Last element is A10. The element before that is A3, right? And that is the question we are asking. So last element is definitely AI, right? What was the element just before? What is the element in the increasing subsequence just before it? And now there are not just two options. There are I options. Yes. So one option is, maybe there is no previous element, right? That's also a possibility, right? Maybe the increasing subsequence is just AI. If everyone before me is greater than me, then I can't choose any of them. It's just me, right? That is one possibility I need to consider. So max of 1, yeah, or AI is chosen. The previous element could be AA minus 1. That is one bag. So this is previous element is AA minus 1. Then I have another bag. This is the previous element is AI minus 2. Then I have another bag in which the previous element is AI minus 3. Like this, I have I minus 1 different bags, and the last bag basically being the second last element is A1. Yeah, so that you see that I'm breaking this bag into I minus 1 sub bags, smaller bags. Okay. Now let's just focus on, say, the second bag, right? The second bag basically has all those increasing subsequences in which the last two elements, so it's an increasing subsequence. I don't know its length, but what I do know is that the last element is AI, that is definitely the case, and the element before it is AI minus 2. Yeah, all such increasing subsequence I'll put into this bag. But now what happens if AI minus 2 is greater than AI? Then there won't be anything. I mean, if AI minus 2 is greater than AI, then this bag is basically going to be an empty bag. Yeah, it's going to be an empty bag. Right. In particular, if I'm at some j, if AJ is greater than AI, then AJ could not have been the second last element in my increasing subsequence. I hope this makes sense. In which case, I don't even consider it. So I'll only consider those j such that AJ is less than AI. Okay. And if AJ is less than AI, I'll have all the increasing subsequences where AJ is the second last and AI is the last element. I consider all those subsequences and that is put into the jth bag. Yeah. And the question is, what is the longest amongst all of them? And now the point is just that if I take out AI is common to all of them. I take them out. I basically get all increasing subsequences which end at AJ. And what is the largest amongst all of them? It's just dp of j. And so the max in that bag will be 1 plus dp of j. Yeah. So that's it. So now I just take max over all such j's. So basically dp of I now just becomes max over 1 comma. Now look at all j where AJ is less than AI. Amongst all that things, consider 1 plus dp of j. Maybe there are no such j's, in which case it's just 1, right? But if there are some j's, consider all such j's and consider 1 plus dp of j and take the max amongst all of that. That is stored as dp of I. Yeah. Yes, so this is going to be an n square approach. That's absolutely right. Yeah. So the j part is just that j is so I have this increasing subsequence. I know these are all increasing, so this is less than, less than, less than. I know the last element is ai. The question is which is the second last element, and if the second last element is aj, then I'm saying that the longest such increasing subsequence is 1 plus dp of j, right? Now do you see why the definition tweak helps us? Because now I know that dp of j ends at aj, and now I can compare aj and ai, right? Which is why the tweak of the definition helps us. So now I can tweak that. Now I can compare this and just take 1 plus dpj, and now I take over max over all such j, and I also take this 1 at the end, and that just gives me dp of I. And the implementation is just first consider dp of 1 and dp of 2, write it as a base case, then write a for loop from I equal to 3 to n, and now I need another inner loop where j runs from 1 to I minus 1. Yes, so j has all those different possibilities, and inside that I write if aj is less than ai, then max equals max of whatever, answer equals max of answer comma 1 plus dp of j. Yeah, and then this answer is basically stored as dp of I. And then what is the final answer? The final answer is going to be max over all the elements in the dp. It's not just dp of n, right? Because dp of n will only have those increasing subsequences which end at the last element, but that need not be the case. I can end wherever I want in the original problem. So I just need to take max of dp1 comma dp2 comma dp3 all the way up till dpn. Yeah, and that's going to be the final answer. No, Shayan, dpi will definitely contain ai because we tweaked the definition of dp to say that it ends at ai, which is why it works. So with 1 plus dp, 1 plus, why 1 plus dp of j and not this dp of j? Because ai is there, right? Dp of j will give me the length of this, but then I'm shoving in ai at the end. So the length of the new sequence is 1 plus the length of this is 1 plus dp of j. Yeah, definitely we'll share some implementation of this. Nipun, we need to check for that constraint, because otherwise we could have a condition like this. Where was that? Yeah, I mean, I might be taking 11, 12, 13, 14 and then 2, which doesn't work. Okay? That's why we need to have that check as well. Cool. So what if AI is the second last? That's fine. That will be considered in some other AI in the future. That'll be considered in the future. It's just not considered now. Right now, I'm going to consider only those things where AI is the last element. Yeah. Or second least. That's fine. That's totally fine. We don't care about the actual values. dp of I has this condition that AI has to be the last element. Right? That's just how our definition works. And it just turns out the actual whole problem works with this extra constraint. Yeah. Cool. Okay. I hope that was kind of helpful. We'll definitely share implementations of this on Discord. I might hopefully by tonight itself. And yeah, please feel free to ask any questions on Discord. There'll be lots of people to help you out. Yeah. Thank you. See you all. Bye.